we've seen that in the lattice of set partitions, every interval x comma y is isomorphic to a product of lattices of set partitions. So it's isomorphic to a poset of the form pi k1 cross pi k2 cross dot 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 pi kr for some integers k1, k2, kr. Now I want to establish a similar result for intervals in the lattice of non-crossing partitions. But firstly, let me explain to you why this may not be as simple as in the case of just partitions. So consider, for example, the interval that lies between 1, 2, 3, 4 and 1, 3, 2, 4. So in the lattice of partitions of 4, there would be 3 things in here, and we would have 1, 3, 2, 4. So there would be 3 here. And they would be just obtained by clubbing. So 1, 2, 3, 4, 1, 3, 2, 4, and 1, 3, 4, 2. And this therefore is isomorphic to pi 3. Set partition of set 1, 2, 3. But now what happens if you look at non-crossing partitions? This 1, 3, 2, 4 is no longer a non-crossing partition, and so if you're working in the lattice of non-crossing partitions, this is what the interval looks like. It only has 4 elements. So this is no longer isomorphic to NC3, but in fact you can show that it is isomorphic to NC2 cross NC2. You should try to do this by yourself. Now let me explain the general case, but again using a slightly more a bigger example. So here in this figure on the left, you see 2 set partitions. The black lines denote the blocks of the set partition Y. The red lines denote the blocks of the set partition X. And it's clear from the figure that both X and Y are non-crossing partitions and that X is a refinement of Y. And now we're interested in understanding the interval X comma Y in the lattice NC12. And the first thing to note is that if you have an element in this interval, so it would be a non-crossing partition that lies between X and Y. Then each block of U would be contained inside a block of Y. And so each block of U can be studied inside one of these 3 smaller pictures, which are the blocks of Y. And each block of U would actually be a non-crossing partition of the block of Y that it lives inside, provided of course you preserve the order on the elements of that block. And so what we do is we break up this interval into pieces, one according to each block of Y. So far this is quite similar to what we did while studying intervals in the lattice of all set partitions. So we just break it up, and so the first block had 4 elements. We pull it out, and now we know that all these elements are the same block of Y, so we forget about the Y part and we only keep track of the X part. So these are the blocks of X that were in the first block of Y. And I've also done a renumbering. Instead of numbering them 9, 10, 11, 12, I've renumbered them 1, 2, 3, 4. I've done the same with the second block. I have just separated it out, and I've renumbered the numbers 1, 2, 3, 7, 8 to 1, 2, 3, 4, 5. I have removed the black lines and I have retained the red lines, which show which block of X, what the blocks of X that lie inside this block of Y look like. And the same with the last block. And here Y breaks up into the 4, 5 and 6 are all in different blocks of Y, of X. And so this is just a discrete set partition. And what we conclude from this is that this interval is actually isomorphic to three intervals in smaller non-crossing partition lattices, namely the intervals 1 2 4 3 comma 1 hat, 1 hat being the whole uh, the trivial set partition of 1 2 3 4, and then 1 2 3 5 4 comma 1 hat, and then the discrete partition comma 1 hat in NC3. So this is the first step in decomposing, but we're not quite there yet because we also want to make this 0. And this is where the difficulty happens. You can show that these things will not always decompose the way they would if we were working um, with set partitions, as I showed you already at the beginning of this lecture in an example in NC4. So what we do is we use the involution phi, not the involution, the order reversing function phi on the set partitions. So here what I've done is I'm going to apply phi to the first set partition with 4 parts, 1 2 3 4. I'm just sort of rearranging it, so I have 1 2 3 4. 2 and 4 were joined by a line in the original, and now I write 1 2 3 4 again in a staggered form, and I find that phi of 1 2 4 3 is 1 4 2 3, and because phi is order reversing, what I get is 1 2 4 3 comma 1 hat under phi goes to 0 hat comma the set partition blocks 1 4 and 2 3, and we do the same thing with the other blocks, and we transform the intervals with right endpoint 1 hat into intervals with left endpoint 0 hat. But now once we have intervals with left endpoint 0 hat, it is very easy to so now we have reached this step where we saw that using phi we are able to convert these intervals with right endpoint 1 hat to intervals with left endpoint 0 hat. But then again, once you have this, the same technique that you would apply for pi n kicks in, and you can show that this is the same as NC2 cross NC2 by just breaking apart the blocks 1 4 and 2 3, and here you would get there are 3 blocks. You would get one of size 2, another of size 2, and one of size 1. So you get NC2 cross NC1 cross NC2, and here you just have one block of size 3, so you get NC3. So, but of course NC1 is just a singleton poset and it contributes nothing to the product. So I can conclude that this interval here is NC2 cubed cross NC3. And let me just summarize this whole example in terms of what happened in a little more formally. So the theorem that we have demonstrated here is that every interval in NCN is isomorphic to a product of the form NCK1 cross NCKR. And the proof proceeds in 3 steps. Step 1, you start with the interval x comma y, and you show that it breaks up according to the blocks of y. Where L is the number of blocks of y. And these would be in some set partition, non-crossing partition lattices. So I guess I could say where lambda 1, lambda 2, lambda L are the sizes of the blocks of y. This was the first step where we just took our non-crossing set partition and separated out its blocks. And then step 2, we use the involution and show that x comma 1 hat is isomorphic to 0 hat comma phi in any NC lattice of non-crossing partitions. And then finally we are able to decompose the 0 hat comma, well, here I should have said phi x. This will be isomorphic to a product of I goes from 1 to m, 0 hat comma 1 hat, NC mu I, where mu 1, mu 2, mu m are the sizes of the blocks of X. So that's the proof.